Hello, today I'm going to tell you about the consensus-halving problem for a constant number of agents. This is joint work with Argyrios Deligkas from the Royal Holloway University of London and Aris Filos-Ratsikas from the University of Liverpool. So let me start by introducing the problem. So consensus-halving is a fair division problem where we have a divisible resource represented as the 0-1 interval. And you can think of this as a cake, as a piece of land, or any other divisible resource that you care about. And we have agents that have valuation functions over that interval, telling us how much they like different parts of the resource. So in this picture, we have these essentially density functions of the valuation functions. And the idea is that if you want to find out what the value of some subset of the interval is for the first agent, the blue agent, you just have to look at how much volume, how much blue volume there is in that subset. So we have these valuation functions for the agent. And what is the goal? The goal is to find a consensus-halving. A consensus-halving is a partition of the interval into two parts, I plus and I minus, such that there is a consensus amongst the agents that these two parts have the same value. So all the agents agree that the two parts have the same value, and formally that means that for all agents I, the value of I plus is equal to the value of I minus. So let's take a look at a few examples to get a better grip on the problem. So in the first example, we just have these three agents with these valuation functions, which are essentially identical for all three agents. And in this case, it's very easy to construct a consensus-halving. You just cut through the middle of the valuation function, and then the two parts, I plus and I minus, have the same value for all three agents. Bit of a more complicated example, again with three agents. This time they have different valuation functions. Now, if I go and put a cut over here, the two resulting parts have the same value for the blue agent, the first agent, and also for the second agent, the green agent, but not for the red agent, who believes that the left part has more value. But this is easy to fix in this case by adding an extra cut over here and considering this partition. Now the middle part has the same value as the union of the two leftmost and rightmost pieces. And so this is a consensus-halving. So in this example, we had to use two cuts for three agents. Is it possible that we might have to use more cuts than this? And the next example shows that yes. So if you take the three valuation functions to essentially be non-overlapping like this, like in this example, then it's easy to see that actually you have to cut every block once, which means that you have to have at least as many cuts as there are agents. A natural question to ask at this point is, can it get any worse than this? Is it possible that I might have to use more cuts? Clearly, this example generalizes to any number of agents, and it tells us that for n agents, there is some example where we have to use n cuts, but is it possible that we might need more? And here we have the consensus-halving theorem, which essentially tells us that no, this is the worst case. The example on the previous slide is the worst case. There's always a solution using at most n cuts, where n is a number of agents. So this theorem can be proved by using a topological fixed point theorem, a pretty famous one, which is called the Borsuk-Ulam theorem. And as a result, this existence theorem, it holds for very, very general valuation functions, not just the very simple additive piecewise constant valuation functions that we had in the examples, but much, much more general valuation functions. So in computer science, we're interested in studying the computational complexity of problems associated to this consensus-halving problem. And the first natural problem to study is what is the complexity of computing a consensus-halving with the minimum possible number of cuts for this instance. And it's not too hard to show that this problem is actually NP hard. And so perhaps a more interesting question that we could hope would be more tractable is to say, okay, then what is the complexity of computing a consensus-halving that uses at most n cuts, where n is the number of agents? And we call this the consensus-halving computational problem. So the idea is that here we know by the consensus-halving theorem that there exists a consensus-halving that uses at most n cuts. So let's just ask for that. Let's ask the algorithm to compute any such consensus-halving, not necessarily the one that uses the least number of cuts. Now, the interesting thing about this is that this problem cannot be NP-hard unless NP equals co-NP. So let me say a bit more about this. The reason for this is that this consensus-halving problem lies in a computational class called TFNP, which was defined by Megiddo and Papadimitriou around 30 years ago. So this class TFNP contains all total NP search problems, namely problems that have three properties. First of all, they are search problems, which means that we're looking for an actual solution, not just a yes/no answer. It's not a decision problem. Second, the problems are in NP in the sense that given any candidate solution, we can verify if it is indeed a solution or not in polynomial time. And finally, the problem is total, which means that for any instance, there exists at least one solution. And in the case of consensus-halving, this is given by the consensus-halving theorem. So if a problem has these three properties, then it is a TFNP problem. TFNP is quite interesting because it lies between the search versions of P and NP, and it is believed to contain many hard problems. But how do we provide evidence that a problem in TFNP is hard? So first of all, no TFNP problem can be NP-hard unless NP equals co-NP. This essentially follows from the definition. So NP hardness is off the table. It's not an option for providing evidence of hardness. What would be the next best thing? It would be to prove that some problem is TFNP complete, but it's also believed that TFNP doesn't have complete problems at all. So what can we do to provide evidence that some problem in TFNP is hard? What Papadimitriou proposed around 30 years ago is to study the landscape inside TFNP, to study subclasses of TFNP that do have complete problems, and to classify the problems that we care about in terms of these classes. So I have pictured some of these subclasses here, but I'll just say a little bit about that. So PPAD is mostly famous because it captures the complexity of computing in Nash equilibrium. PLS has been very successful in capturing the complexity of various local search optimization problems. And the class that we will care about here for this talk today is PPA, which you can think of as containing all TFNP problems where totality, namely the existence of a solution, follows by this Borsuk-Ulam theorem, this topological fixed point theorem. Now recall that consensus-halving, the consensus-halving theorem can be proved using Borsuk-Ulam, and so that means that our consensus-halving problem lies in PPA. So a few years ago, a breakthrough result by Filos-Ratsikas and Goldberg showed that the consensus-halving problem is in fact PPA complete. So it is complete for this class associated to Borsuk-Ulam. Let me just take a minute to explain what PPA completeness means. What should it mean, the fact that the problem is PPA complete? So first of all, mathematical interpretation is that the consensus-halving theorem is in a certain sense equivalent to this topological Borsuk-Ulam theorem. And from a computational perspective, it means that the consensus-halving problem is unlikely to admit the polynomial time algorithm. And this is because in particular, it's as hard as computing in Nash equilibrium, but also many other problems that have been proved complete for PPAD. Let's take a closer look now at this theorem. One interesting thing to note is that consensus-halving is PPA complete, but this holds for n agents. In other words, the problem that they consider, the number of agents is not fixed, but it's given in the input. And in fact, the hardness holds when we have a high number of agents. So the question that we asked in this project is, what happens if the number of agents is fixed? What happens if it is some constant like 2 agents or 3 agents, 4 agents? What can we say about the problem then? Does it become easy? So let me take an even closer look at this hardness result of Filos-Ratsikas and Goldberg. First of all, it holds for very simple valuations, namely piecewise constant valuations that are given to you explicitly in the input. And in fact, this result has been improved at EC last year to show that it holds even if you just consider so-called 2-block uniform valuations. In other words, valuation functions that have at most 2 blocks of value, so very, very simple valuations. And the hardness result also holds if you consider an approximate version of the problem, which is called epsilon consensus-halving, where the idea is simply that you're given some epsilon and you're just looking for an epsilon approximate solution, namely the value of the part I plus and the part I minus, They just have to be epsilon close, not actually exactly equal. So a relatively simple observation is that if you consider a fixed number of agents and this model of valuations, namely explicit piecewise constant valuations, then the problem can be solved in polynomial time. And the algorithm is not that interesting. It's essentially a combination of enumeration and linear programming. But what that tells us is that this is not an interesting model in the case of a fixed number of agents. And so to study this problem with a constant number of agents, recall that the consensus-halving theorem holds for extremely general valuations. So what we do is we start from the top, from the most general types of valuation functions, which we just call general valuations. So these are just functions that map subset of the interval to some real value, and the only condition is continuity, essentially Lipschitz continuity of that function, and that's it. So extremely general valuation function. And then we consider also a special case of those valuations, which are monotone valuation functions, which have the added property that if A is a subset of B, then the value of A should be at most the value of B. So this is also a very natural property. In terms of how these valuations are represented in the input of our computational problem, we consider two models there. First of all, the white box model, where the functions vi are given as polynomial time algorithms. In other words, they're given, we have full information about these valuations. We have a polynomial time algorithm that can just evaluate the valuation. And then a second model that is quite nice for these kinds of problems, which is the black box model, where we just assume that we have query access to the valuations. And in that case, we just measure complexity in terms of the number of queries. Whereas in the white box model, it would be just standard computational complexity. Let me just mention in passing that our results also hold for an appropriate generalization of the Robertson-Webb model. So I'm happy to say more about this at the poster or in some question. So without further ado, let's move to our results. So we show that the complexity of epsilon consensus-halving for a constant number of agents is essentially given by this table. So the rows correspond, first of all, the first row is general valuations, the second row is monotone valuations, and the columns give you the number of agents. And let me start with an executive summary of the results. So for general valuations, we show that the problem is easy for one agent and hard for two agents, hard for three agents, and more agents. And for monotone valuations, we show that the problem is easy for one agent again, but also easy for two agents, and it becomes hard only after three agents or more. So there is a difference in where this transition from easy to hard happens. For general valuations, it's when you go from one agent to two agents, but for monotone valuations, you can solve the two-agent case efficiently. So it's the transition from easy to hard is when you go from two to three agents. So now let me go over this table in a bit more detail. So for one agent in general valuations, it turns out that a simple binary search approach solves the problem. And so that means that in the white box model, you can solve the problem in polynomial time. And in the black box model, namely the query model, you can solve the problem with order of log 1 over epsilon queries. And just to give an idea of what we should compare this quantity to, I've put down there on the right that there's always a brute force algorithm that solves the problem with 1 over epsilon to the n queries, where n is the number of agents. So having an algorithm that solves this in log time or even polylog time is what we consider to be an efficient algorithm, as opposed to doing brute force. So this is for one agent. What happens when we move to two agents? There we show that the problem in the white box model is PPA complete. And in the query model, we get this 1 over epsilon lower bound on the number of queries, which again, we see as being inefficient. And so in that sense, for two agents, the problem is hard. These hardness results generalize to three agents and more in a natural way. And so let me move to the monotone case now. So the easiness result for the positive result for one agent automatically transfers to the monotone valuation case. simply because monotone valuations are a special case of general valuations. But now, the interesting thing is that for monotone valuations, there is also an efficient algorithm for 2 agents, which is based on essentially a nested binary search approach. And this gives us, polynomial time solvability for this case in the white box model, and the polylogarithmic upper bound in the query model. So as I showed earlier on this other slide, the problem now becomes hard for 3 agents with monotone valuations, and we again have a similar 1/epsilon lower bound for 3 agents. In terms of techniques, I won't say much, but let me just say that the results are obtained through what we call efficient black box reductions. And this essentially means that we using a single reduction, you get both the hardness in the white box model and the hardness in the black box model. So we get both the PPA hardness and the query lower bound just with a single reduction, by making sure that this reduction is an efficient black box reduction. Let me just say one more thing for the hardness results. The reason why in the monotone valuations, the problem only becomes hard for 3 agents is that in order to obtain monotone valuations, we need an extra dimension when we prove the hardness. And of course, this is not just because the reduction is not optimal or something like this, because we have the positive result for 2 agents. So there is a fundamental reason for this. Let me just finish by mentioning future directions, or in fact just one future direction that we think is quite important. So I've just pasted in the table from before here. We have these general valuations, then we have the monotone valuations that are special case of general valuations. And there is another class of valuations that's a special case of monotone valuations, and which is actually a very important class, which is very widely studied, which are additive valuations. So additive valuations have the added property that if 2 subsets A and B are disjoint, then the value of the union of those 2 subsets should just be the sum of the values of the individual subsets. So this is also something very natural to have in an evaluation function. So what we would like is to add additive valuations to this table. What can we say right now? Well, we can say that, of course, the positive results from monotone valuations automatically also hold for additive valuations. So we get this here, but we don't know what happens for more agents. Does it become hard already for 3 agents, like in the case for monotone valuations, or do we need to go to more agents? Is it easy for 3 agents? And we hope that our technique of efficient black box reductions can help in resolving this question as well. So this is all for now. If you want to find out more about this, please visit our poster. Thanks.